Hey, what's up everyone? Welcome to Stoichiometry and Solutions Part 4. Today is all about solution chemistry. So let's start by defining solution. So a solution is a homogeneous mixture where a substance called the solute is dissolved in another substance known as the solvent. There's actually a lot here, so let's first break down that first bit. A homogeneous mixture. A mixture is literally a combination of two or more things. It's basically anything. And there's going to be two different types of mixtures. The first one is going to be a heterogeneous mixture. Heterogeneous mixture. I think I spelled that right. And it's going to be a heterogeneous mixture is a mixture where you can tell the difference between the two things that go into making it. So an example would be like a cookie. So if I give you a chocolate chip cookie and I add some chocolate chips in there, that chocolate chip cookie is a heterogeneous mixture. And that's because the two components that go into making it is the dough and the chocolate chips. I'm going to write CC. But the thing is, you can tell the difference between the dough and the chocolate chip. You can tell that this part is the dough and that part is the chocolate chip. On the other hand, you have a homogeneous mixture. Homogeneous mixture. An example of a homogeneous mixture would be something like Kool-Aid. So you know that the Kool-Aid is just the Kool-Aid itself and the water. It's a mixture of these two different things. But the thing with the homogeneous mixture is that you can't tell the difference between its components. So if I give you a glass of Kool-Aid, you can't tell the difference between the water particles and the particles of Kool-Aid. They all just kind of blend together and look the same. So this is a homogeneous mixture. This would be considered a solution, but this would not be considered a solution. And that's because a solution is only a homogeneous mixture. Another example of a homogeneous mixture would be salt water. So salt water looks something like this. It's water with sodium ions and chloride ions dissolved within it. And that's because when you dissolve salt, it's going to dissociate into sodium ions and chloride ions. And in this case, the solvent is the water and the solute is the salt. But how do you know which is which? How do you know that the water is the solvent and the solute is the sodium chloride? Well, the solute is usually the substance that's found in smaller concentrations. So in this case, water is a lot more abundant. There's a lot more water than there are sodium chloride ions. And most of the time, whenever you have a mixture with water, water is almost always going to be the solvent, and whatever else it's dissolving is going to be the solute. A common thing you might have heard is that water is the universal solvent. And that's because water has a capability of dissolving a lot of substances. So most of the time, if you see water in a solution, water is almost always going to be the solvent. Okay, that's a solution. So a solution is a homogeneous mixture where a substance known as the solute is dissolved in another substance known as the solvent. Now, your solution is going to be different based on the properties of the solute and the solvent. And one of the properties that we care about is going to be the phase. So let's look at what happens when we have a phase, when the solvent is a certain phase, when the solute is a certain phase. And let's start with a gas and a gas. So let's say the solvent is a gas and the solute is a gas. The solution is going to generally be a gas. It's always going to be a gas. And an example of this would be something like air. Air is a solution. And there's a lot of things that make up air, but two of the things that we can look at are oxygen and nitrogen. In this case, the solvent is the oxygen because oxygen is far more abundant in our atmosphere than nitrogen. So if you have a solvent that's a gas and a solute that's a gas, your solution is also going to be a gas. Now, what if you had a liquid and a gas? Well, your solution is going to be a liquid. And an example of this is like seltzer water, which is just water with carbon dioxide in it. Another one would be liquid and liquid producing a liquid, something like alcohol with ethanol dissolved in water. Liquid and a solid producing a liquid, something like salt water where the solute is the salt and the solvent is the water. And this is a kind of weird one. If you have a gas and a solid, the solution is going to be a gas. And an example is camphor in nitrogen. You might notice a pattern here, and it's that the solution, the phase of the solution is going to be almost always dependent on the phase of the solvent. And this goes back to the fact that the solvent is the more abundant component of the solution. So the solvent generally determines the phase of the solution. Okay, not all solutions are created equal. Solutions can be different based on how much solute you give it. Like, for example, if we look at putting like sugar in coffee, you can have a lot of sugar or you can have a little sugar. In other words, in your coffee, you can have different concentrations of sugar. And in a solution, you can have different concentrations of solute. But it's inconvenient to talk about them in kind of qualitative terms where we talk about a lot of solute versus a little solute. We prefer to talk about them in qualitative ways. And the way we do that is by putting units on concentration. And we have two different units. The first one, molarity, is the most common one. And it's going to be the moles of solute per liter of solution. It's signified by this big M here. And again, it's moles of solute per liters of solution. It has like a little brother, and it's called molality. And so molality is moles of solute per kilogram of solvent. And that's really important because you'll realize in molarity, you have liters of solution, focus on the solution bit. And in molality, it's kilogram, but it's kilogram of solvent. Again, molarity is far more common than molality, but molality is used for certain properties of solutions that we'll talk about later. Okay, let's get a bit of practice with these concentration units and specifically molarity. So what mass of NaOH is contained in 250 mils of a 0.4 molar sodium hydroxide solution? First of all, this 0.4 molar is going to represent that in 1 liter of solution, you have 0.4 moles of NaOH, sodium hydroxide. So if you have 250 mils of this solution, you have 0.25 liters of solution. And we can use this to find how many moles of NaOH we're dealing with here. So we know that we have 0.4 moles of NaOH per 1 liter, and we have 0.25 liters. And so what we realize is that we have 0.1 moles of sodium hydroxide. The question asks us for the mass of the sodium hydroxide. So how do we turn moles into mass? Well, we multiply by the molar mass. So we have 0.1 molar NaOH, and we want to multiply by the molar mass. So 1 mole of NaOH is about 40 grams of NaOH. So the mass comes out to 4 grams NaOH. And that's how you use the concentration to help you determine different things. Concentration is a really fundamental idea, and it's used all throughout chemistry, especially molarity. So it's really important to know this little bit. All molarity represents is that in 1 liter of a solution, you have that many moles of that solute. One last thing about solutions is dilution. So dilution is the process of decreasing the concentration of a solute in a solution. So if you have something like alcohol, some people water down their alcohol because I guess it's just too strong. What you're doing is that when you're adding the water, you're adding more solvent. So what happens is that your concentration goes down. Dilution is a really common thing in lab settings. So when you have a lab and you need to order chemicals and stuff, you want to order chemicals in high concentrations. And the reason you do this is because you can always decrease the concentration of a solute, but you can never increase it. So if you have a really concentrated solute, you can create many different types of solutions with different concentrations based just using that same solute. A formula that's really helpful when dealing with dilution is M1V1 equals M2V2. And it represents that the concentration of the first solution, the concentration times the volume of the first solution, is going to equal the concentration times the volume of the second solution. So what do I mean? Let's look at a problem. How many milliliters of 0.5 molar copper 2 sulfate solution must be added to 160 mils of water to achieve a 0.30 molar copper 2 sulfate solution? Okay, so we know what the first solution is. So solution 1 is going to be 5.0 molar copper sulfate, but we don't know the volume of it. So let's just say it's X liters. And we also have another solution, solution 2. And we know that solution is going to have a 0.3 molar concentration of copper sulfate. And we also kind of know the volume. We're told that we have 160 mils of water, but whatever we add, however many milliliters of copper sulfate, 5 molar copper sulfate solution we add, we must add to that volume. So the volume actually comes out to 0.16 plus X liters. And again, this is coming from the fact that we're adding 160 mils of water to solution 1. So the volumes are additive. You have to add them up. And now we can use M1V1 equals M2V2. M1 is 5 molar. So M1 and V1 are going to be based on solution 1, and M2V2 is going to be based on solution 2. So M1 is 5 molar, V1 is X liters, M2 is 0.3 molar, and V2 is 0.16 plus X liters. If you have trouble solving for X, it helps to just forget about the units for a second. So if you forget about the units, the left-hand side becomes 5X, and the right-hand side becomes 0.048 times, plus 0.3X. Now isolate X, so 4.7X equals 0.048, and you just divide both sides by 4.7. And that isolates X all by itself. And at the end, X comes out to 0.0102. And this is in liters, but the question asks for milliliters. So we multiply this value by 1,000 rather, and that tells you that you have 10.2 milliliters. So you would need 10.2 milliliters of a 5.0 molar copper sulfate solution, and you need to add that to 160 milliliters of water to achieve a 0.3 molar copper sulfate solution. And that's dilution. All right, that's all I have. I hope you were able to learn something, and I hope to see you later. Thank you.